Okay, good afternoon, everyone. Thank you so much for coming to our Engage session. My name is Mariah Pulver. I'm a Communications and STEM Engagement Lead here at Goddard. Today, we are very excited to see people in person and virtually for this Engage session all about ILLUMA-T, which is NASA's next step in laser communications. Laser communications can provide numerous benefits to missions. And right now, the Exploration and Space Communications Projects Division is demonstrating that through missions like ILLUMA-T and LCRD. Before we begin, I have just a couple housekeeping reminders for everyone. First, we'll have a live question and answer session today with our wonderful panel members. So if you're in the audience and you would like to ask a question, there are microphones on each side of the auditorium. And if you're online, you can post your questions in the chat on the right-hand side throughout the panel discussion, and then we'll go through them all at the end. Now I'd like to introduce Katie Schauer, our moderator for today. She is our Strategic Communications Lead for the Exploration and Space Communications Projects Divisions. Take it away, Katie.
Thank you, Mariah. So thank you all for coming to the ILLUMA-T Engage session, like Mariah said. We're first going to get started off by talking to our panelists and learning what their names are and what their roles are. Do you want to get started, Zach?
Sure. So I'm Zach Gonnsen, the lead system engineer for ILLUMA-T. Is Mike working? So my role is really a lot of coordination between all discipline engineers and making sure we both have our science goals, meeting all of our external interfaces, and that all the pieces play together well. And hopefully as we go through testing, we find any issues, and then we can have a successful mission once we launch.
Nice. Trisha?
Hi, Mike seems to be okay. So I'm Trisha Randazzo. I am the lead mission integration and test engineer. I work really closely with Zach. We have very similar goals. Mine is focusing more on our external partner interfaces. And so for ILLUMA-T, we have kind of two partners we work with, the International Space Station and our partner out in geosynchronous orbit, LCRD. So one of my main objectives is to make sure that we integrate well with their systems, and also to make sure that our people are trained up so that when they are called upon to operate our terminal on the space station, it is able to be operated.
And Chetan.
All right. Thank you, and thank you all for coming today. My name is Chetan Sayal. I'm the project manager for ILLUMA-T. Been here at Goddard since 2004. And my role is overall programmatics, control and management of ILLUMA-T. So under programmatics comes the schedule, the budget, and sort of overseeing the technical implementation of the project and making sure that we have a capable team and that we can deliver under our commitments of schedule and cost.
Awesome. Well, thank you all for introducing yourselves. So as you probably heard, we are doing a payload called ILLUMA-T, and it's using laser communications. But just to give people some background information, Chetan, what is laser communications, and what are the benefits of that technology?
Okay. So laser communications is a relatively new technology. Most of our satellites and payloads that are on orbit right now use RF communications that are radio frequency communications. Laser communications uses lasers to communicate that data back and forth instead of using traditional RF comm. The benefits that you get out of laser communication is you can get faster data rates, much faster than what you would get in RF comm. And that allows you to be able to transmit more data. So as our science instruments are growing and the capability of what we're capturing is growing, laser communication provides us a faster way to bring that data down and to disseminate it and learn from it. So that's the benefit of laser comm. There are other benefits, laser comm packaging, i.e. the components that make up laser comm are smaller and lighter and use less power than traditional systems. So if you are building a spacecraft, instead of putting up larger arrays of RF comm equipment, you can put in smaller and lighter subsystems to get that data down faster.
Okay, and so what I'm hearing is that there's a lot of benefits here. What why do we need more data in a single transmission? What is the overall goal there?
So just to kind of put it in perspective, so JWST that launched recently in the last year, the amount of data that is coming down from JWST is substantially greater than something the predecessor Hubble Space Telescope brought down. So to be able to get that larger data set down is why NASA is going into laser communications, to be able to enable that larger data set to come down. Just to kind of imagine, to put it in perspective, as your TVs have grown and your resolution on your TVs has grown, the amount of pixels that a TV can show has increased, and so do science instruments on board spacecraft, right? So that larger resolution requires you to bring that additional data down.
Awesome, thank you so much. Zach, a question for you. What is the ILLUMA-T payload?
Yeah, sure, I can give a little overview. So, basics, we're an ISS payload. So we are going to the International Space Station and are mounted on the external part of the station, which means, there's the spots where the astronauts live and work, and a lot of that stuff is pressurized and in atmosphere, where we are removed from that and are outside the station in vacuum and operate completely robotically. We don't have really much interaction with the astronauts on a day-to-day basis. You can almost think of us as similar to an antenna for RF comms that are existing on the ISS now. But the nice thing that we get to do is hook into the ISS's network so that we can send data from the station down to the ground. And we do that via the LCRD satellite that Trisha mentioned earlier. And LCRD is located up in geosynchronous orbit, so it is essentially a fixed spot over the Earth as the Earth rotates. And underneath it, the ISS will move and orbit the Earth roughly every 90 minutes. So as the ISS orbits, we will come in contact with LCRD and able to downlink data for a long period of time before we lose signal to LCRD and go behind the Earth. And the benefit of that is we get to download a lot of data for a long period of time and show an operational case where we can orbit in a low Earth orbit where the ISS is, and use a satellite up in geosynchronous orbit that's fairly far away relative to where the ISS is, and send data back to the ground. And that's really how we will get to demonstrate laser comms operational scenarios. And on a day-to-day basis, as the ISS needs to downlink data to the ground, we will get to demonstrate that capability.
Awesome. Okay, thank you for that description. Trisha, what is ILLUMA-T's process for transmitting and receiving data? So how does the information taken in and used?
Yeah, so ILLUMA-T has, as we've been talking about, we're using with lasers, right? And so ILLUMA-T and its partner LCRD out in geo-orbit, they're both using something called an optical module. And this optical module allows us to create the laser inside the payload and then shoot it out. And then that laser will connect with its partner, in this case LCRD, in geo-orbit, and once it makes that connection, then the laser link is locked and you can send the data through. There are various components on both sides which will understand what the laser light is doing and change it back into information that we're used to on our networks, like electrical signals versus optical signals. But overall, that's kind of like how the engineering side of the receiving and transmitting works.
Okay, so what I'm understanding is that there's a terminal on the International Space Station, it's collecting data, it's sending the data to LCRD, LCRD is sending that data down. So that's NASA's first end-to-end laser system, correct?
End-to-end can sometimes be relative, but for our perspective, in the laser comm world, yeah, it's kind of the first time that we're taking a laser data which begins in orbit someplace, whether it's LEO orbit or GEO orbit, and it's being relayed from another satellite back down to Earth. So most of the optical comm that NASA and other space agencies in the world have done have either just been orbit to orbit or maybe just a single signal down. But this is kind of the first time where you have your user in space, which is the game changer here. Your user's in space, it's being relayed down through the LCRD relay, and then it goes through Earth's atmosphere until it reaches its optical endpoint, which is a ground station. And then once it's on Earth's surface at that ground entry point, then kind of the surface network takes over and the data ends up at its desired destination.
Okay, great. And what kind of data is ILLUMA-T transmitting, will ILLUMA-T transmit when it's up there?
So it can do a lot of different kinds of data, but the idea is that it'll be a full audio-visual kind of data.
Awesome. So back to you, Chetan. What can missions expect if they adopt optical communication systems?
So I touched on this a little bit already. If missions adopt optical comm, the standard RF communication system requires a lot of power, requires a lot of weight, and both power and weight end up being big design drivers for a satellite to be able to launch it into space. So with laser communication and the packaging and the weight being smaller, you're actually making them slightly cheaper to produce and get it into orbit. And the added benefit is also, as I said earlier, you're increasing the amount of data that the science instruments can do and downlink. With the reduction in the weight, you can actually put in higher capability instruments because again you've minimized the weight of the communication systems, so you can then reallocate some of that weight into instruments and getting higher capability out of the instruments.
Okay, that sounds great. And how long will ILLUMA-T work with LCRD?
So the mission that ILLUMA-T has, it's a technology demonstration mission where we're trying, as Zach and Trisha have stated, we're showing and showcasing this technology of a user in LEO to communicate to a relay satellite to transmit the data down. That overall mission is a 6-month operation mission. Where we get to show the links, show the stability of the links, show what kind of bit errors that we get off of that link, show the max data rates that we can get and how well those are characterized. All of that happens over a 6-month period.
Okay.
The other added benefit that we get out of this is we get to show in an operational sense how this end-to-end system works.
Okay. So ILLUMA-T is working with LCRD. LCRD actually launched in December 2021. Do you want to tell us a little bit about LCRD, Trisha?
Yeah, so for a little bit of background, before I joined ILLUMA-T, I did a similar role on LCRD in the mission team, but I was a support engineer, I wasn't the lead. So LCRD was kind of NASA's effort to begin this process. I think the panel in the room here can see that there's the technology roadmap going by. But LCRD and ILLUMA-T are just one step in this technology roadmap that NASA has been developing. And so when LCRD was being developed, its goal was to act as a relay, which required it to have 2 optical terminals, one to gather, one to send, kind of, both can do both. But the idea is that one would speak to one user and the other one would speak to another user, and this way it acts as a relay. And so it is a payload on another satellite called STP-SAT-6, and it is in geosynchronous orbit, launched in December, like you said. And for the last year, it has been in orbit, understanding how the laser link through the atmosphere is changing throughout the Earth's seasons. It has a lot of support that's been going on to understand and characterize that behavior. And one of its next steps will be to interact with a LEO user, which will be ILLUMA-T.
That's awesome. It's a really cool mission. Before we keep going, I wanted to ask, are there any questions from the audience?
Yes.
Awesome, great. Let's ask them. Let's get some questions from the audience.
Okay. We have 2 questions from the audience right now. The first one is the assumption correct that lasers may be able to increase the data rate from Mars to about 10 times what we receive from radio?
I don't know the exact figure, whether it's a factor of 10 or not. The nice thing is that the speed of light is all the same between RF and laser comm. So the increases come from the speed directly, but it's really how much data you can send with a certain amount of power. So lasers are higher in the electromagnetic spectrum, so you can basically encode a lot more data, and with the same amount of power, with smaller or basically large amounts of data you can get sent, and it all depends on the size of your antennas and your size of your telescopes, and as Chetan was alluding to, the nice thing about laser comm is all that can get shrunk down, and you can kind of pick and choose what you want based on the mission. If you want to send more data, you can make a larger telescope, and that would be a lot smaller than you would need from an RF antenna, for instance. So there's a lot of trades you can make, and you can probably get to that 10x depending on how much power and size you want to put in, or you can have the same amount of data transfer with less power and less mass.
Yeah, the analogy I like to make for learners is that if you can imagine you're driving in your car and you stuff your car full of stuff, but you're going 25 miles an hour, and however much stuff's in your car is how much stuff you're taking. That's like your data. Well, laser comm is like, instead of you stuffed a train full of gear, or a car full of gear, you stuffed a train, right? Your train is still going 25 miles an hour, but it can just hold so much more information in it. And that's kind of what laser comm is doing. That's why it's faster.
Yeah. That's a great analogy. We're also testing laser comm in the future on the Deep Space Optical Communications Terminal, which will be on the Psyche mission launching next year, and that is going to an asteroid. So that'll try to test some of the deep space capabilities of this technology.
Awesome. The second question is, will optical communications be part of the future with the TDRS fleet?
So I can try and answer this. So it's not currently in the baseline, but what is being attempted to show here as a technology demonstration mission is a TDRS-like capability using optical comm, right? So TDRS is, the analogous to TDRS is LCRD, where LCRD is a relay satellite, and any satellite that communicates with TDRS today is using RF communications. That can either be in LEO orbit or near Earth orbits. ILLUMA-T would be the first optical terminal that is communicating with LCRD, so it's kind of showing that same linkage that you have with TDRS using optical comm.
So for example, right now the International Space Station communicates to the Tracking and Data Relay satellite system, which is in the same orbit as LCRD, and then that communicates down to Earth?
No, not exactly. So LCRD is in geo orbit, which is about 35,000 kilometers out. TDRS is in kind of this middle orbit, and it has, I think, nine total TDRS satellites, but only 4 or so are used, or 5 are used at a time. A couple are retired or spares. And so those TDRS satellites are in a different orbit than both LEO and LCRD.
Interesting, thank you.
Yeah, they are definitely in a different orbit, but it's a constellation. But the concept of a relay is the same.
Okay.
Yep.
Yeah. Interesting. And did we have any other questions from online?
Nope, that's it for right now.
Okay, great. Please feel free to put your questions in the chat if you have any. Now we're going to move on to the next portion of our questions, which is the challenges questions, my favorite section. So Zach, what are the challenges of putting a terminal on the International Space Station?
Oh boy, where do we get No, I mean, luckily the ISS is actually a great place to go. They do a lot for a payload. They provide a lot of services that if you go other routes, you basically would have to provide yourself. In terms, they provide power, they provide a data interface, they kind of take care of the infrastructure for attaching a payload. So that's a great benefit, but the flip side is you then have to comply with everything that they're doing. You basically need to fit into their certain spots. So there's volume constraints, there's mass constraints. You have to communicate over certain protocols. So the way you send housekeeping and telemetry over to the ISS network, all that's very well controlled. As well as the safety of the astronauts. Of course, we are going to a manned satellite, and even though I alluded to earlier, we don't have really direct interactions with the astronauts. We obviously cannot do anything to put them in danger, put the spacecraft in danger. So we go through a whole safety process and several very detailed safety reviews to make sure that everything we're doing is not going to damage anything on the space station. Even from just a power surge, or up to having the laser hit any surfaces that it shouldn't. So.
So during their EVAs, the lasers won't be active, right? The extravehicular activities, right?
That's true. Whenever an astronaut is outside the station and when a vehicle is docking to the ISS, we will not be powered on.
Okay. Awesome. And then I have a question for each of you. What is a recent challenge that the team overcame during the integration and test phase of this mission?
I'll Chetan start.
Let's see. So I'm going to touch on the integration test period for ILLUMA-T actually occurred during the start of COVID, right? So as the entire country and NASA and Goddard Space Flight Center were all adapting to the precautions under COVID. We were starting our INT phase, and there were a lot of evolving challenges that came in on how people could safely build hardware. Obviously, hardware can't be built in your own garage, within your four walls, right? So the hard part of the INT phase of a mission is people actually have to come into Goddard to build the hardware, so we had to understand the evolving precautions that were being put in place at the workplace and make sure that there was enough PPE that was available. We were making sure that people were distancing from each other, limiting the number of people that could be in a given space at a given time, and still attempting to stay within cost and schedule bounds, right? So that was definitely quite a challenge. The safety of the personnel was highest. So we obviously went a lot slower and less efficient, but that was by design.
Okay. Very interesting. Yeah, I know a lot of workarounds had to be done because of COVID, so. You want to take a turn?
Yeah. So as one of the INT leads, there's a lot of challenges. And just to give folks some background who are maybe a bit new to the spacecraft. So when you make a spacecraft, there's this life cycle that you'll hear about, the spacecraft development life cycle. The words that NASA uses is it goes from pre-phase A to phase E, and that whole thing covers your spacecraft life cycle. That's from conception of what the mission's going to do to finishing your mission and sending your spacecraft either into graveyard orbit or burning in the atmosphere or some other disposition. So when it gets to INT, we like to joke that INT gets the short end of the stick because everyone else gets to spend all the time and money figuring out designs, but then they want everything done in a day. So when it gets to INT, this is where the rubber hits the road. This is where everything is coming together, and you finally have to get it to work. So there can be a lot of challenges in and of itself from just the pure nature of what INT is. For our team recently, one of the things that is difficult for our unique project is we have so many partners, right? We have our partner in LCRD, and we have our partner in the space station. And so one of our difficulties recently was trying to test what our acquisition is really going to be like. In the INT world, we try to do everything as flight-like as possible. We test it as close to the way that we can fly it. Naturally, because we're on Earth's surface, we have limitations, right? I can't actually test acquiring 35,000 kilometers away, right? But you can do similar things. And so the strategy that usually INT takes is take as much of that flight-like thing as possible and do it as you can. Usually that ends up meaning doing things in parts. Maybe you'll get a couple parts together, but you aren't going to actually test the entire thing until you're in orbit for the first time. So it is a challenge, especially because of the space environment is so much different than the Earth environment. So one of the things we had to do recently was to try our acquisition with LCRD. In our language, we call that a mission readiness test. there's various ones of those. But for ours, we wanted to try to make sure that we had our ground system programs command the optical module to point to the place it needs to point to acquire with LCRD, and then show that it can slew throughout a contact, maintaining the appropriate position, and then finish its slewing motion once the contact ends. So we started this test, and it started at the right time. It slewed for the right amount of time, but it pointed in completely the wrong location. And so what that means for me is that, like, at the mission level, because you're working with so many different components, it's like, well, where's the problem? And so now you get to have everyone talk, and it's a lot of talking. I know a lot of times people think engineering is not talking, but there is so much talking. And so there's a lot of talking to try to figure out which part of the system is at fault here. Maybe there's only one. Maybe there's 5 places that this problem's occurring, right? And so you have to get all the people in the room, you take off little splinter meetings, and you figure out where is it most likely to be. And that's where you look your efforts in first. So we had a couple of people trying to figure out if there was something wrong with the instructions sent from the ground system program, or if there was something wrong with the receiving computer on board the terminal. So those teams went off and they tried to understand what was going on. They ran their own simulations. They checked their math, zeros and ones, positives and negatives, matrices. You know, it's all sorts of those good math skills you learn in algebra class. And so after several iterations of trying to figure out what the problem was, it was kind of determined that it was where the system thought it was in space that was wrong. You can kind of think of that as like the spacecraft's proprioception. So there was an update that we had missed, and we needed to make that update, and so we got the update. We retried the test, and then it was successful. It pointed to where we wanted it to go, or at least it commanded it to where we wanted it to go, and then we were able to solve that problem. And it seemed like it took 6 months, but really it started on Halloween and it finished before Thanksgiving, but it still felt like a lot of time.
Well, that's a really interesting example. It's really fun to hear about like the intricacies that go behind the INT phase, because for me, at least from my perspective, it's just like the INT phase. Like I don't really know what happens in that phase other than that you pass a lot of tests, but that's really cool to hear about. What about you, Zach?
Well, I can give another example that's ongoing currently for our INT testing. You know, as Trisha alluded to, you try to test everything you're going to see, both during launch and on orbit. And one of the major things that you have to do is obviously launch on a rocket that has a lot of vibration and really looks fairly violent when you watch them on TV. So the payload has to survive that. And the way we do that is do vibration testing. We have a lab here at Goddard that we go on a table and basically shake the instrument up to what we expect to see it on launch. And we have, you know, after everything gets assembled, we go into this testing and we have all the engineers kind of check, you know, make sure that we think everything's going to survive, of course, going before the test. And then, you know, the test is a chance that we can kind of verify that everything's looking good before we launch. And during our most recent vibration test, we did have a failure in a plumbing line. So as I mentioned before, on the ISS, one of the things they provide to you is a cooling system. And that's basically how we get our heat out of our payload so we don't overheat ourselves. We have electronic boxes that turn on and they heat up, and then we usually essentially use a cooling loop to pass the heat away back to the ISS, where they, as part of the infrastructure, luckily take care of the heat for us and then provide us a nice cool liquid. It's basically a cooling system for your computer that you don't have to worry about how it actually gets cool. So that's a benefit, but the downside is we have to make a cooling system inside the payload that both connects to all of our hardware and can survive all of our launch loads. And that's what we discovered in our most recent test, which is, thank God, why we test this payload and before we go to launch. And with that, you basically go through a whole redesign effort and failure review boards to understand, one, what has happened. You look back through all the structural models, all the components, material certifications to make sure what you have you know, is what you expect to have. You get, luckily the nice thing about Goddard Space Center is there's several experts on almost everything you can imagine. So, you know, being here and being part of NASA, you get to really pull a lot of expertise in and get some experience of, you know, what things we possibly need to change and redesign. So that's actually where we are right now, is in the redesign and retest phase prior to our launch coming up later this year. We are making design changes, making component changes, so that we can go back into testing and pass them before we launch. So
Okay, well, it sounds like you guys are working really hard.
it's always an invention, that's for sure.
Yeah. So, Trisha, you kind of brought this up before about the atmosphere, but what are the atmospheric impacts on optical signals, and why do we need to understand that?
Yeah, so it's great. We with lasers have discovered that they don't like water. We like water as people, we drink water, we swim in it, we ski on frozen water, but for lasers, they don't like water. When a laser interacts with water, it pretty much attenuates it, which is another way of saying it disperses it strongly, to the point where you lose your signal, and now you can't talk, you can't get your data, right? And if you think about it from like a planetary perspective, it's kind of interesting because most of our planet's atmosphere is nitrogen. It's not even water. Like 78% is nitrogen, and then like 2% is water. But that's enough water to impact a laser communication. And so that's kind of one of the reasons why it's been so difficult to get laser comm to work for spacecraft. When you think about it, if you remember those days of dial-up, your phone was using your internet was using like the phone line, which was super slow, but at least, you got a page every 10 minutes. And then that changed, right? We got better internet, and that pretty much what that meant was that our internet went optical, right? We have fiber optic cables in the ground. It's great. But when we're trying to use that same technology for space, we have to use lasers through the atmosphere. We don't get to just like build a cable to the sky. Like that doesn't work structurally. And so we have to do it through the atmosphere, and we have to deal with the atmospheric particles and the atmospheric composition. And water is the main propagator of a laser's light, like disperser of laser light. And so first we had to get over that technical challenge of, can we just get a laser to work through the atmosphere on a standard day? Like normal atmospheric pressure, temperature, humidity, blah, blah, blah. And then once our abilities were able to overcome that engineering difficulty, now we were like, okay, well, if we can work a laser through normal conditions, how do we avoid, or how do we mitigate having large quantities of water happen? And that would be like a storm, or maybe it's overcast all day, or maybe it's a hurricane. And so pretty much what our solution is, well, let's just avoid it, because we can't go through it. So what we do is we kind of have these two ground stations, optical ground stations available to us. One's in Hawaii, one's in LA. And the idea is that if we are having a constant contact with our optical ground station in Hawaii, and a storm comes by, then we'll just switch to the one in California. The idea being that if there's bad weather in one place, there should be better weather in the other. And so in that way, you kind of practice this handover. And Chetan alluded to that as one of the operational things that ILLUMA-T is demonstrating, is the ability to hand over a reliable service. And the idea of that's not new. Your cell phone does it when you're going from a radio tower to a radio tower. Your phone just hands off immediately. There's no issue there. And then that's kind of like what we're practicing with our optical ground stations, is how do we do that? Because even though the idea is very similar to the radio towers on Earth, because we're doing optical in space, there are differences, and those are what we need to understand and figure out what those problems are and figure out solutions to them.
That's interesting. Also, it must be nice having ground stations in Hawaii and California. Those are pretty sunny areas, so hopefully not too many clouds for you to avoid.
Except for,
Yeah. And then how are NASA's optical ground stations breaking ground for future optical networking systems?
Yeah, so it kind of goes right into that. So we don't have very many optical ground stations on Earth's surface as a human population. And so the reason why is because it's new, and generally new technology like this is very expensive. And so this is kind of the proving ground, or the experimental platform, or guinea pig, if you will, for understanding how do we need to really build an optical ground station so that it is reproducible at a cheaper level for the masses. And so that's what's really impressive about these ground stations is they're difficult to work on because now that we have things in orbit, there's problems we couldn't anticipate that we need to solve. And so there's a lot of real-time problem solving happening. And there's also better understanding of the optics themselves, and being like, oh, when we designed these optics, we really didn't think about this, and now we need to go back and maybe add a few more things here or there. And so it's really giving the opportunity for the technology to improve to the point where it'll be able to be used at a wider scale.
Nice.
And I can actually add to that, as these two ground stations are networked together, and it really demonstrates, as Trisha was getting to, the switching, and that can really be jump-started to, having more ground stations, right? You have more ground stations around the globe, you get better communications. That's kind of the infrastructure that our FCOM has now. There's, several deep space networks all around the globe, and if you demonstrate this swapping between two ground stations, kind of real time, that LCRD and ILLUMA-T get to do, then you kind of keep adding to that. And once you get more ground stations, you get a lot more flexibility and how many satellites you can have with optical comm, where they are. You have the benefit of going directly to ground stations from a satellite, even though you have a shorter span of time. If you have more ground stations, you can kind of swap between them basically real time as you fly over one, then fly over to the next. And that's kind of all the things our FCOM has been doing for many decades, and this is the opportunity to show that optical comm can do the same thing.
That's really interesting. So hopefully one day there will be more ground stations supporting more optical communications missions.
And then weather also becomes less of a concern, right? You have multiple ground stations, you can kind of avoid the storm in over California.
There's not going to be a storm that covers the whole planet's surface.
Hopefully not.
No atmospheric rivers.
And then I think our division is actually working on like a low-cost optical communication terminal, which is more commercial oriented, right? Do you guys know anything about that?
Just a little bit. I know LCOT, it's happening just down the road out here. They're kind of in their beginning phase to understand it, but eventually they would like to be working with projects like ILLUMA-T or LCRD so that they can have a laser connection there.
Right.
And for those folks who aren't familiar with Maryland, it rains a lot here, so I'm interested to see how that works.
Yes. Yeah. So I think that uses like commercially available parts, which might bring the cost down a bit. So
Exactly.
Okay, so kind of in closing, this is for you, Chetan. What are NASA's plans for a future laser comm mission? And actually, our picture up right now shows our roadmap, which is good.
I think that's a good picture. So there's two pieces to this, right? All of this work that we're kind of talking about comes in under SCAN. That is our sponsor over at headquarters. They're responsible for the entire agency of providing communication networks. So both RF systems and what we're talking about here of optical systems. SCAN is infusing and demonstrating optical communications, right, with LCRD that launched in December 21. They also recently launched T-Bird, which is terabit size connections from a user in LEO orbit. ILLUMA-T is next. ILLUMA-T we've sort of talked about a little bit. They're showing the relay aspect, what you would see in a traditional TDRS type system for RF communications. We talked a little bit about DSOC. DSOC is a payload that's on the Psyche mission, and it's attempting to show optical communication over larger distances as it travels out to Psyche, still showing the same optical downloads that we would get. And then following that, we also have O2O, that is an optical terminal that is being put on Artemis 2 that will be able to provide us the live feeds from Artemis 2 when that flies. So NASA Scans in particular has created this roadmap that you can kind of see flashing through the screens here of the infusion points to show optical communications through this diverse portfolio and various distances. So that's what we're doing in space itself. On the ground, and you've heard this a little bit, right? We've got two optical ground stations that are currently operational, communicating with LCRD and being able to show that transition from one ground station to the other, understanding the atmospheric effects off laser comm. There's also conversations in international terms on putting other optical terminals around the rest of the world. And as you touched on, there's low-cost optical terminals that are being planned to bring down the cost of an optical terminal by using more commercially available parts and sort of reducing the footprint cost of a ground terminal.
Okay, great. And then, do you have any online questions we wanted to ask? Awesome. Awesome.
Okay, yep, we have quite a few online questions.
Oh, good.
So one of the first ones, Trisha, you were talking to this a little bit earlier, talking about testing the pointing accuracy of ILLUMA-T. And one of our questions was, are the pointing accuracy requirements more stringent for lasers than for radio frequency?
I would say overall, yes. So for radio frequency, for those who remember like being with your TV and like finicking with your antenna to get a better signal back in the day, that is like a really wide, I would say, because the radio signal itself is larger. Radio waves, they can be miles long, their wavelength. For the laser light that we're working with, it's much smaller wavelengths, and so because of that kind of physical property, by definition, you have to have a tighter accuracy for your pointing. The analogy I like to make here is like when ILLUMA-T is trying to make its acquisition with LCRD, it's like if you're standing on Earth's surface and you're trying to shoot a bow on a bullseye that's traveling and it's 10 miles away from you, but you have to actually shoot a bullseye. Like that's kind of the kind of accuracy we're trying to get.
Wow.
Yeah.
Wow.
The next question is asking, could this technique, laser communications, be used for missions going to further away targets like Titan or Europa? And if yes, what components of ILLUMA-T or the existing systems would need to change to make that happen?
So I think I tried to answer that with DSOC, right? DSOC is our trailblazer when it comes to going further distances away from Earth. So DSOC, deep space optical
communications.
Thank you. Sorry, work for NASA. Too many acronyms. So DSOC is going to Psyche, right? And we're attempting to show the larger distances optical communications in that front.
Yeah.
And I can add a little bit to the changes that we'd have to make. Right, so basically as you get farther out, similar to an RF facility or capability that you basically grow the telescope. So we have, it's on the screen at the moment, so it's very convenient. We have a telescope that's 10 centimeters in diameter. So basically the farther away you get, you want to collect more light. Similar to lenses on a camera. The more light you collect, the higher basically the farther away you can get and the more data you can transmit. So if we go out to, for instance, Mars, right, we can increase that size to a 20 centimeter telescope. And the farther out you go, you can increase the size, but you can also increase the power of the laser. That's something DSOC is doing in comparison to ILLUMA-T. They have a higher power laser. So we have a 3-watt laser, which is a lot more, if you think of like a laser pointer, right, those are kind of in the milliwatts. But if the farther out you go, you can have a lot higher power. So I think DSOC is somewhere around the 20-watt area. So if you were to go out to those farther planets, you would both increase the size of the telescope and as well as the power that you could transmit.
And I think the only other thing that I'd kind of add, the benefits that you get with optical communications going into further away from Earth, right? Those benefits still exist. So even though you have a larger telescope or slightly more power that's needed to drive your laser, it's still substantially less than what you would do on an RF communication system.
Awesome. One of the next questions, we'll define an acronym for everyone, Chetan's favorite activity. How does ILLUMA-T compare to one of the other missions you mentioned, T-Bird? So for our audience, the Terabyte Infrared Delivery System, which we launched in May 2022.
So T-Bird's a CubeSat, so it's actually significantly smaller in size and power. It's also a free-flying orbit, so as I mentioned, we're attached to the ISS, so we're not particularly flying on our own. We're attached to the host spacecraft of the ISS. Where T-Bird's CubeSat is in low Earth orbit, and it is actually talking directly to the ground. So we are using a relayed satellite, whereas T-Bird points down to the ground. And I think Chetan alluded to, it can go, the T is for terabit speeds, so it can go very fast, and there's a lot of challenges with going fast in terms of just reading that data and sending it out very quickly. You think of most computers and USB drives don't really run that fast. So that's one of the things they get to demonstrate. And then having direct to Earth is another thing that they are demonstrating that it's a little different than from what ILLUMA-T is doing.
Nice. And yeah, just to add to that, T-Bird did 4 terabytes of data in under a 5-minute pass back in December. So the data benefits here are significant for science and exploration missions.
That's a lot of movies.
Yeah. Yeah, I think they counted it's like 900,000 minutes of music, like technically.
It's a lot. If anyone in the audience here has a question, reminder that you can use the microphones. We do have more questions from online though, so don't worry.
I have one last question.
When is ILLUMA-T launching and what is it launching on?
So ILLUMA-T target is to launch on SpaceX 29. That is still being refined, so it's not a definitive, but SpaceX 29 is a resupply mission to the ISS that's going to launch in December of this year, December of 2023.
And that's a Falcon 9, right?
That's a Falcon 9.
Yeah.
Yep, sorry.
No,
So,
you're fine.
on the resupply missions, they have the Dragon capsule that goes to the ISS, and we are technically in the trunk of the Dragon. So we are unpressurized during launch, which means as soon as we launch, the atmosphere will depressurize as we get up into space, whereas inside the Dragon it's pressurized. And then Falcon 9 will take us up the first 2 stages, and then Dragon capsule will take over and actually dock us to the ISS. Once we're on the ISS, robotic arms, the cannon arm will actually remove us from the trunk and install us onto our position outside the ISS.
Nice.
And that's just a plug too for updates on launch, and to watch launch you should follow us on Twitter at NASA LaserCom, so you'll always know the most recent updates about all of our LaserCom missions there. Our next question is ILLUMA-T capable of downlinks as well?
Yeah, so I can take that one. So ILLUMA-T is both uplink and downlink, and so its partner also is uplink and downlink. That's important because just because you can do something, if your partner can't do it, then you're both failing. So yes, LCRD is able to do uplink and downlink. Therefore, ILLUMA-T can do uplink and downlink of data over its optical link.
Yeah, and the max data rate that we're looking at bringing down to the ground through LCRD is 1.2 gigabits.
Awesome. The next question, are Hawaii and California NASA-owned ground stations, or are we working with other organizations to borrow access?
I don't know who actually owns the OGS1 and OGS2.
Yeah, I actually don't know the answer on that. I know they are NASA funded, but I don't think it's a 100%, but I'd have to go confirm that.
I think the OGS1 in LA is with JPL, so I think that one is NASA through and through, yeah. I'm just not sure about OGS2 in Hawaii.
I think OGS2 is shared with another U.S. government agency, if I'm correct.
Some homework for us to look into. We don't know all the answers. Always something to learn. That's all we had online right now. Do we have any questions from the audience?
I have a closing question.
Go for it.
So what is your favorite part about working on ILLUMA-T? A pretty easy one. End on a happy note.
I actually, I'll can kind of go first. I actually like the diverse group of people that I kind of work with, right? Not only, as you can kind of see, work with engineers, I work with financial folks, schedulers, risk managers. It's just very diverse group of people that I kind of work with, coming from very diverse backgrounds. It's not like you have to have an engineering degree to be able to work at NASA, right? You can work, you can have a history major or an English major, right? And still come in and work in NASA and interact with the great folks that are here. So that's my best part of working Illuma.
That's very true. I majored in journalism.
Yeah, I would say, I mean, there's so many great things about working for ILLUMA-T and at NASA. I'd be hard pressed to almost pick just one, but I also really like the people. It's really nice because through a lot of my education degree, training, you'd come up with a question and it'd be difficult to find the answer just because you couldn't find the expert or whatever. But at NASA, like, there's so many experts. So it's like, if I have a question, I don't have to spend 5 months trying to find an answer online. I can just email a person or walk to their office and be like, hey, I was wondering about this, and then they give me an answer. And that kind of access to such skill is really nice. But I would also want to say I really like the mission of ILLUMA-T. I was a kid when the space station first started getting built, and that was so cool. And I was like, oh, if I went into the space industry, how cool would it be to work on something that had to do with the space station? So just the mission itself was also like a self-fulfiller for me.
Wow.
Yeah.
Well, you, Zach?
I of course agree with both their answers. And could add, you know, as Trisha said, right, the working with the space station is wonderful, right? There's so much complexity to basically that machine that's been built and is being operated on a day-to-day basis of, you know, learning more about that, learning how payloads go on there, how they work, and, you know, basically how the whole ISS works, you know, in general, with the teams around the country and around the globe, and all the operation centers and all the coordination that's done. Kind of get an insight to that is great to have. And, you know, in addition to just the ISS side, right, LaserComm in general, you know, in my mind is really the next step that we're going to make for comm across the board. Right, we have all these upcoming great missions, you know, to the moon, you know, possible bases on the moon. You've got the gateway. You've got all these reasons why having more data is going to be beneficial to NASA. And, you know, as cameras right back in the 70s, you had little 200 pixel cameras. Now you've got 4K, you've got James Webb sending back amazing photos. Right, the requirement on sending more data back to the ground is not going to go away. And, you know, as we go farther out, as the missions get even more extensive and you know, more really ambitious, right, LaserComm is going to be there to really help them out and help get the data down. Right, you take the complexity away from being on board computers. You know, you don't have to compress data. You don't have to do fancy algorithms on board. You can pretty much send everything to the ground. Right, we humans are better at computer vision than things that can be done on board. We have supercomputers on the ground that can do the processing for that data. So, you know, in my mind, being a part of that transition, that we can really take comm forward and get future science missions, you know, the benefit. It's a good feeling.
That's awesome. It's really fun to hear about. Do we have any last questions?
Nope, that's it. So I think we're ready to close out. Thank you everyone for attending today. Thank you so much, Katie, for moderating, Chetan, Trisha, and Zach for participating. This was a great opportunity. Reminder to all of our attendees that these Engage sessions are held monthly. So it's a great opportunity to learn more about the missions and projects going on here at Goddard. So please tune in next month. I'm not quite sure what it is, but check back on the website. And if you want to watch this again, the recording will be shared online too. So thank you all so much for attending.
Thank you.
Thank you.
Thank you all.